In this video we're going to look at direct and inverse proportion. Sometimes you might hear this topic being called variation. Let's start off now with direct proportion. So writing this in direct proportion. Two quantities are said to be directly proportional if they're increasing at the same rate. So what does that mean? Well, let's take a job, and in the job I'm going to get £4 an hour, and I'm going to have my wages, which will be W, and the number of hours, which will be H. So let's model this up. My wages will be equal to 4H. So whatever I get paid will be 4 times the number of hours that I do. This is an example of direct proportion. They are increasing at the same rate. So let's go ahead and do some examples. If I worked for 2 hours, my wages would be equal to 4 times by 2, which gives me 8. If I worked for 10 hours, we could see that the wages would be 40. We could work out how many hours I've done if I was given a value for the wages. So for example, if W is equal to 60, dividing by 4, we could see that that was going to be 15 hours. When we're dealing with problems with direct proportion, we can graph these, and all of the graphs will be from the origin. So for example, now W is equal to 4H might look something like so. We could have a quadratic function. So from the origin again, we might have a curve. So it looks something like so. So these are examples now of direct proportion. We can write, if Y is directly proportional to X, we can write the following statement. So this is telling me now that Y is directly proportional to X. We could also write this now as Y is equal to Kx, where K is a constant of proportionality. So in this case, we could say that wages are directly proportional to the number of hours we do, and in this particular case, K would be equal to 4. Most of the questions we're going to do get us to solve for K, the constant of proportionality, and then find other values. So these two things are identical. I think it's easier working with this particular notation, but it's entirely up to you. And some questions will write it like so. So if we said that Y is directly proportional to X, this would be the statement. Sometimes a question might say that Y varies as X. Again, it means exactly the same thing. Or Y varies directly as X. We're going to do a few questions and get comfortable with the notation and move on from there. So there's direct proportion. As one quantity increases, the other quantity increases at the same rate, and we can draw all the graphs from the origin like so. So let's have a go at a question. It says, using the data given in the table, check whether the statement given could be correct. So what this is saying is Y is proportional to X. So I can write that Y is equal to Kx. If I take the first one right here, I'm going to substitute these values in and find K. So if I put 39 in, that's going to be equal to K multiplied by X, which is going to give me K times by 3, or 3K. So from this, dividing both sides by 3, we can see that K is 13. Therefore, we could write Y is equal to 13x. All I'm doing is simply substituting K back into here. So does that work out? Well, let's have a look here. If we now substitute in X is equal to 7, Y is equal to 13 times by 7, and that does give us 91. So it's true for that one there. We would check it just here, and is Y equal now to 13 lots of the value of X? Well, 10 times by 13 is 130. So that is going to be, Y is going to be equal to 143. So yes, that statement could be correct. So this shows direct proportion. If we wanted to graph this, this would be a very straightforward graph. We would have now the origin, and we've have a straight line with a gradient of 13. So it looks something like so. So that would be my graph. So let's go ahead and do that. So this is going to be y, so y, and this is going to be x. And the gradient of that line, m, is going to be equal to 13. We won't always get x. We might get x squared, we might get x cubed, we might get the root of x, but we'll look at that as we go. So y is proportional to x. Okay, this time we're told that s is proportional to r, and we need to fill out this table. So if s is proportional to r, I can say that s is equal to kr, where k is the constant of proportionality. We found that before. K is 13 here. It's just the multiple. So the only bit of info we can use is this one right here to find the value of k. So I'm going to substitute this in. We're going to have 30 is equal to k times by r, which is going to give me k5 or 5k. Dividing both sides by the 5, we can see that k is equal to 6. So now I'm going to substitute this in and rewrite the statement. S is equal to 6r. So this now gives me my relationship between S and R. They are directly proportional. So if I think now all I need to do is substitute in R is equal to 2. I'm going to do it without doing that. 6 times by 2 is going to be 12. 6 times by 3 is going to give me 18. And then 6 times by 7 is going to give me 42. And again, we have a linear graph. This is just a straight line. We're plotting points on a straight line. All we've done is found the value of a constant of proportionality and gone from there. Okay, we've now got a wordy question. So this one says the cost C of building the roof of a house is proportional to the area A it has to cover. The roof costs £6,000 and covers an area of 36 metres squared. In part A, we need to find the relationship between C and A. So what we can say is that C is proportional to A. You often don't have to write this. I'm going to write it anyway, so we can say that C is equal to K, where K is a constant of proportionality, multiplied by A. I'm now going to substitute in what we call the initial conditions, or what we're given. So the cost is 6,000, so 6,000 will be equal to K multiplied by the area, which is going to give me 36. So to find K, we're simply going to divide 6,000 by 36. You can use a calculator for that. 6,000 divided by 36. We end up now with 500 over 3. So that gives me the value of K. So let's go ahead and write that in. I'm going to leave it now as a fraction, as it's a lot easier to work with. So just checking all that looks good. So the cost of the building is now going to be proportional to the area, and 6,036 metres squared. So we can write now that C is equal to 500 over 3 multiplied by A. And that is what we call an exact fraction. So all we need to do now in part B, this is the relationship. So that's the relationship found. C is equal to 500 over 3A. We need to find the cost of a roof to cover an area of 27. So 27 is A. So we're going to have C will be equal to 500 over 3 multiplied now by a value of A, which is going to give us now 27. You can do this on a calculator if you wish. 27 over 3 is going to give me 9. 9 times by 500 should give me 4,500. Let's just write in C as 4,500. And then I would say that it's going to be 4,500. So using my pound notation afterwards, let's put that in. And again, we could work that out on a calculator if you were unsure. Okay, the next one, we've got a roof cost £7,500. What area does it cover? So what we need to do is work this one backwards. So we can say that 7,500, that is the cost. We're solving for A, the area. And that simply means that we're going to divide the 7,500 by this answer here. So if I do that, 7,500 divided by my answer is going to give me 45. So we can see that A is going to be 45. So that tells me now that it would be 45 meters squared. So we can see now that we've got a straightforward problem with direct proportion or variation, and we simply had to take it out of a wordy question. Okay, this one says if v varies directly as r cubed and v is equal to 24 when r is equal to 2, find the value of v when r is equal to 3. Okay, this is a case of direct proportion, but we've got a cubed term. So I can simply write this now as v is equal to k r cubed. If you wanted, you could start with v is going to be proportional and directly proportional to r cubed, and then write the following statement. This one, I'm just going to write it like so. So let's put in what we call the initial conditions. This will allow us to solve for k, which is our constant of proportionality. So 24 is equal to k multiplied by 2 to the power of 3. 2 to the power of 3 is 8, so that would give me 8k. Dividing both sides by 8, we can see now that k is going to be equal to 3. I'm now going to substitute this back in here and say that v is equal to 3r cubed, and that is the relationship. This will allow us to solve for any other problems where we have either v to find or r to find. So this time now we can go ahead and find v because we're given r. So we can say that v will be equal to 3 lots of 3 to the power of 3. That's 27. 27 times by 3 is going to give us 81. So that is what we have. We simply substituted that in and we've gone ahead and found them. So nice and straightforward, entirely up to you on that, on how you want to set it up, but that would be a nice question to do. So this time we might be given, for example, let's say that v was equal to, let's change this around, let's say v was going to be equal to, we'll go for 243, make it nice and easy. So 243, and we wanted to find r. Then all we would do is take this statement here, and we could say that 243 was equal to 3r cubed. Dividing both sides now by the 3, that's going to give us 81 is equal to r cubed, and then we would take the cube root of 81. So the cube root of 81 is going to be equal to r, and we can find that on the calculator. So let's go ahead and do that. We'll take the cube root. So now we can put the cube root in like so, and we can put in the cube root of 81, and that's going to give us 4.33 correct to 3 significant figures. So 4.33, and that would give us the value of r, and that is the 3 significant figures. So we can work this backwards and forwards. Okay, so that's a nice example there. Right, let's look at this one. We're going to fill out the table. Y is directly proportional or varies as x. So if you see y varies as x, unless it has a word inverse in it, we assume it to be direct. And we can see this is direct anyway. So what I'm going to write is that y is equal to k, and then we're going to have the root of x. We need a value for x, and we need a value for y to find k, and this is what we're going to use. So 1 is equal to the square root of 4, which is going to give me 2k. So all I've done is plugged in the initial conditions. So from here we can see that k is equal to 1/2. So we can rewrite our relationship as 1/2 the root of x. So I'm going to use this for all of the other values to simply go ahead and find them. So if we look at this one, if I take the square root of 9, that's 3. 1/2 of 3 is going to give me 3 over 2. So we can write 3 over 2 or 1.5. I prefer working with fractions. All I've done is substituted in now 9 here. The square root of 9 is 3. 1/2 times by 3 will give me 3 over 2. If I take the square root of 10, that's 100, that's going to give me 10. 1/2 of 10 will give me 5. So we'll end up now with something looking like that. Okay, if we look at the next one, we're going to have a value of y. So what we need to do with this one is work it backwards. So y is 6, and that's going to give us 1/2 the root of x. So I'm now going to multiply both sides by 2. 12 is equal to the square root of x. To solve for x, we need to square both sides of the equation, and that is going to give me that x is going to be 12 squared, so that's going to be 144. So that's what we end up with, 144. If I wanted to draw this graph, let's go ahead and do that, we'd have something, you wouldn't be expected to do this, but our graph, again, we would go ahead, draw this, and it would start at the origin, and it would look something like so. So it come up, round, like this, and gradually do something like that. It would increase in size. So another example of direct proportion. Okay, we're told now on this one, a zoologist assumes the mass of an elephant is proportional to the cube of its height. A young elephant has a height of 1.5 meters and a mass of 400 kilograms. Find the mass of the elephant when it has grown to a height of 2.4 meters. Let's just pull the maths out of this. Typical wordy question that we really don't need to worry about. The mass now is proportional to the cube of its height. That's all we need to know. The mass is proportional to the cube of its height. So let's go ahead and rewrite this. So what we can say is that the mass is going to be proportional using k as the constant of proportionality to h cubed. That's the cube of its height. If it said the cube root, we'd have now the cube root. We now take the initial conditions. We've got a height of 1.5 meters and we've got a mass of 400 kilograms. So if I just substitute these values in, what we have here is 400 is equal to k, and then we'll have 1.5 cubed. You can write it as 1.5 or you can write it as a fraction. I'm going to write it now as 1.5 cubed. So we could find the value of k by doing 400 divided by now the 1.5, which we're going to cube, and that would give us k. So let's go ahead and do that in the calculator. My brain's not going to work that out too quickly. So 400 divided by 1.5 to the power of 3. We can either use this button right here or this one. It's entirely up to us. And that gives us this value here. So that's going to give us 3,200 over 27, or that now as a fraction, or a decimal. I'm going to write it like so. So 3,200 over 27, so let's write this in. K is going to be 3,200 divided by 27. So I'm now going to rewrite this statement with our value of k, which is just the multiple, the constant of proportionality, 3,200 divided by 27 multiplied by h cubed. So we need to find the mass of the elephant. So we need to find the mass when the height is 2.4. So all we're going to have is the mass will be 3,200 divided by 27 multiplied by 2.4 cubed. So all I need to do is just multiply this answer now. So this answer in here, and I'm going to multiply that now. Let's check I've got all of that in. Okay, so I'm going to multiply that by 2.4 to the power of 3, and this will give us our answer. So we end up now with 1638.4. Let's just write this in. So 1638.4, and I'm going to say that that's going to be 1600. So 1640, and that's going to be kilograms, and that is going to be given now to 3 significant figures. Remember, you might look at this and think, well, it's not got a massive, great amount taller, but it's got incredibly a lot more heavier. But that's the way animals work. So don't be alarmed. As long as your math stacks up, be confident. Okay, let's move on. What we're now going to look at is inverse proportion. So if we just write this down, inverse proportion. So inverse proportion. Inverse proportion is a little harder to get your head around but still the same principle. This time, if something increases by a scale factor of k, the other quantity decreases by a scale factor of 1 over k. Let's look at this now in terms of context. If we went to, or someone went to a school prom and they hired a limousine, and it was going to be, let's say the limousine was £100 to hire. So it's £100 to hire this limousine. Now limousines can get a fair amount of people in those big stretched things. If one person pays for it, or one person goes by themselves, it would be equal to £100. If 2 people got in, they would pay 50 quid each. If 3 people got in, they would pay 33.33 ... If 4 people went in, they would get they'd pay 25, and we can see that this is decreasing. So the more people I can get in here, the less they have to pay, and that's an example of inverse proportion. So as one quantity increases by this scale factor of k, the other decreases by 1 over k. And I think that would be the best way of describing it. And if we wanted to write that mathematically, we could say if 2 quantities, let's take y and x, were inversely proportional, we could now use the notation, and remember this shows proportionality, and we'd write it like so. Y is inversely proportional to x. I prefer to write this as y is equal to k multiplied by 1 over x, which we can write as y is equal to k over x, where k, again, is this constant of proportionality. Another way of looking at this is if we multiply x and y, this will always give us a fixed value, which we call a constant. This is where I'm focusing on now at this particular level, but this is interesting nonetheless. So let's do that. So let's just graph what's going on here. So if I looked at the cost now and the number of people, we would have now the following relationship. So this now, let's put the number of people. So we'll have the cost. So let's put the cost of our limo, and this is now the number of people. What we'll see when we have inverse proportion, we'll have a graph that looks something like so. So it'll come round and down. So we can see now that the cost for people is never going to be 0, but the cost will now decrease as the number of people increases. So let's go ahead and look at some questions. Again, all we do is find the constant of proportionality and then solve from there. Okay, for each table of values below, determine whether the relationship given is true or false. So this is saying now that y is inversely proportional to x. Now, sometimes the questions might say y varies inversely as x. Don't be worried about it. It's just more, it's just a different way of putting it. So if this is true, then y is equal to k, where k is a constant of proportionality divided by x. So let's try this one right here. What we're going to do is substitute in 8 and 3. So y is 8, then we've got k, and that's going to be over 3. Multiplying both sides by 3, we can see that k is 24. So if this is true, we can rewrite this now as y is equal to 24 divided by x. So does this one hold? Well, if I substitute in now x is equal to 4, 24 divided by 4 is 6, so this one is true. And just showing that y is equal to 24 divided by 4, y would be equal to 6, therefore it's true. So if I look at the next one, y is equal to 24 divided by x, so 24 divided by 5, that's going to give me 4.8. So y is equal to 4.8, therefore it's not true, as it's telling me it's 4. So if you're offered a question like that, just check the values, find your constant from 1, and then check that it holds for all of the others. So if you'd done this one, instead you would have got a different value of k, and then you'd see that it doesn't work for the others. Okay, so that's a nice, fairly straightforward question. Use the relationship given beside each table to complete and copy the table. So this one, Q, is inversely proportional to P. So I can say that Q is equal to K over P, where K is a constant of proportionality. We need to use this information as we've got what we call the initial conditions. So this will allow us to solve for k, and then we can substitute these values in to go ahead and find q. So let's do that. We've got q, that's 2, and then we've got now k over 32. Multiplying both sides by 32, we can see that k is going to be 64. So now, instead of writing this statement with the unknown k, which is just a constant, this idea of a constant, that value doesn't change. The variables, the things that are going to change, are q and p. K is a constant. So we can now write that q is equal to 64 divided by p. So let's put in p is equal to 8. So q would be equal to 64 divided by 8. So we can see now that that's going to give me 8. If I put in now p is equal to 4, 64 divided by 4 is going to give me 16. If I put 1/2 in, 64 divided by 1/2 is going to give me 128. Dividing by 1/2 is the same as multiplying by 2. So that would fill out the table, and we've gone ahead and done that. Okay, let's have a look at another one. Y varies inversely as x. If y is equal to 1.5 when x is equal to 2, find y when x is equal to 4. So again, let's pull the maths out. Y is inversely proportional to x. So if you want, you could write it in the following notation, or you could take this and say that y is equal to k divided by x, where k is the constant of proportionality. At this stage, I'm going to substitute in these values. 1.5, so 1.5 is equal to k divided by 2. I've taken the initial conditions, or the values we're given for x and y, which will allow me to solve for k. Multiplying both sides by 2, we can see that k is going to be equal to 3. So instead of writing y is equal to k over x, y is equal to 3 over x. And this now is the relationship we have. So we want to find y when x is 4. So y is going to be equal to 3 over 4, which is going to give us 3/4. If it asks us to find x when y is equal to 5, what we could do is write that 5 is equal to 3 over x, multiplying both sides by x, dividing both sides by 5, we'd have 3 over 5. So that is flipping this around. This would be find, and I'll just write this here, find x when y is equal to 5. And that's just turning the question round from the other way. And you might be asked to do that. And you might be asked to do it with a square or a cubed term as well. Okay, let's have a look at this one. Y varies inversely as x squared. So y is inversely proportional to x squared. We need to copy and complete the following table. So we can say that y is equal to k over x squared. It's inversely proportional. If this said now that it was inversely proportional to the root of x, y would be equal to k over root x. If it was x cubed, y is equal to k over x cubed, and we can just fill these in. Again, we need to take the initial conditions for one that we have to find k. So we're going to have y, which is 0.75, so 0.75, or if you like, we could write that as 3/4 as a fraction, will be equal to k over x squared. 2 squared is going to give me 4. So from this, multiplying both sides by 4, for some reason again, k is equal to 3. K isn't always equal to 3, it's just turned out nice that it is in the last couple. So replacing this, now we have a relationship that y is equal to 3 over x squared. Again, the graph would look very similar. If we took positive values now, it would come something like so. So we'd end up with something that looks like that. So what do we need to do? We need to fill out these values. Well, this one's nice and straightforward. If I substitute in x is 1, 1 squared is 1, 3 over 1 is going to give me now 3. If I substitute in x is equal to 3, we'd have 9. We'd have 3 over 9, which is going to give me 1/3. If I substitute in x is equal to 4, we've got 16, and that would give us 3 over 16, which I'm going to write as 3/16. So all I've done is substituted values in. If you wanted, you could do, let's make quite a different one. Let's say we were now asked to find the value of x. So we want to find x when, and we'll have now, when y is going to be equal to, and we'll go for now on here, let's take, we'll take on there, we'll go for 1 over 27. So 1 over 27. So let's see what we get. So we could say now that 1 over 27 is equal to 3 over x squared. So I need to solve this equation, multiplying both sides by x squared and multiplying both sides by the 27. That's going to give me 81. I need to take the square root of both sides. Square root of x, square root of 81 gives me now 9. So we could find x by working it the other way. Okay, so that's now y varies inversely as x squared. Just think to yourself, y is inversely proportional to x squared. Okay, let's do a wordy one. In an electric circuit, the current I is inversely proportional to the resistance R of the circuit. In part A, it says if, when R is equal to 1000, I is equal to 0.5, find the relationship between I and R. All we need to do is pull out the maths from the wordiness. So what do we have? We've got I is inversely proportional to R. And that's nice and straightforward. So it's now a linear relationship. So we've got no square term, cube term, or the square root. And we can write that I is equal to K over R. Again, if you wanted to write now that I was inversely proportional to 1 over R, you're more than welcome. At this level, this statement is perfectly fine. So let's substitute in these values. We're going to have 0.5 will be equal now to K over 1000. Multiplying both sides by 1000, we're going to have that K is equal to 500. So we can write that I is going to be equal to 500, and then we're going to have 500 divided by R. So that now gives us the relationship. So if you're asked to find a relationship, that is the relationship. In part B, if the resistance increases to 1500, what is the current? So if we look at this, the current is I, the resistance is R. So we could say that I is going to be equal to 500 divided by R, which is now the 1500. 500 over 1500 would give us now 1/3. So we'd have now 1/3 of I would be equal to 1/3. So that's what we've got, and that is relatively straightforward. Again, you can do that on a calculator, or you can cancel those. 5 over 15 is 1/3. In part C, it says what happens to I if R is doubled. Remember the relationship. If R doubles, I will halve. As one increases by a scale factor of k, the other decreases by a scale factor of 1 over k. So if R trebled, I would be divided by 3. So when R is doubled, I is halved. And that goes back to our scale factor. And again, if you wanted to write this, you could write now that IR was equal to some constant. And once we know what the constant is, that kind of makes sense. But I don't think this is necessary to go this particular route. It should be fairly intuitive that if we double R, I will halve. So there we go, direct and inverse proportion or variation. Essentially, we just check what the question's asking us, we solve for the constant of proportionality K, substitute it back in, and then go on and solve problems related to that.